So in the previous video, we established this set of equations for the average kinetic energy of a single particle in a gas. One form was 1/2 mv squared, so the kinetic energy equation, where instead of just having regular v, we have the root mean square velocity, which is just a different way of saying the average velocity. It's just finding the average in a slightly different way. And this is also equal to 3/2 times Boltzmann's constant times the temperature. And what's good about this, and what's important, is this has safely established a connection between the average kinetic energy of particles and the temperature of the gas as a whole, which that is the basis for what temperature is, so we want to make sure we have a good mathematical connection there. But you might also recall that in that video I said I was not going to do a derivation there, therefore why I'm doing it here. And the reason why is because it's a little complicated. To do it 100% properly, you would have to do a derivation of the Maxwell-Boltzmann distribution in 3 dimensions, an analysis of it. And to help put that a little bit in perspective, the equation for that is looks something like this. Not real pretty. There's a lot going on there. Kudos to James Clerk Maxwell and Ludwig Boltzmann, two of the greatest physicists who ever lived, who were able to analyze this theoretically and by hand in the 1800s, but we're not going to do that because, long story short, this is above the pay grade of, honestly, most even grad students to do this by hand, so I'm definitely not going to do it because it's way above the purview of this class. Instead, we're going to talk about a more physical derivation, like where do these concepts come from and how can we connect it that way. I'm going to go in more new in advance. The derivation is a little hand-wavy. There's a couple of moments when it feels like we're making a little bit of a logical leap, and that's simply because a real proper derivation really should be taking advantage of this rather imposing equation. So first off, we start with a sealed cube, and in this cube there are a number of gas particles. However, to simplify things, we're going to first start off with only one gas particle, and additionally, it is moving in only one direction, which we see as the x direction. So we're going to focus first on one particle moving in one dimension. And we know when the particle hits the wall, it's going to have a change in momentum in the x direction. And we know previously that the equation for this change in momentum, the impulse equation, is a force times the change in time. And to make things real clear, I'm going to say this is the force in the x direction of the wall on the particle, and that the change in time, because we're going to have another change in time in a minute, so I'm going to say this is a change in time of the collision. So it's going to be a really, really, really tiny amount of time. And just looking at this, because these are elastic collisions, no energy is lost, and the particle has the same magnitude of velocity before it hits the wall and after it hits the wall. It's just going in opposite directions. So if I want to write this out a little more, I would say this is m delta v in the x direction. This whole side is not going to change, so I'm just going to leave it there right now. And additionally, we're going to have that because these don't change magnitude, I could instead just call this minus v to relate it to v, because the speed is the same. So I'm going to get final minus initial, so that would be v minus, v in the x, minus negative v in the x. And if I do that, I'm going to get 2m v in the x direction, and I'm just going to bring this down. It's the force in the x times the time of the collision. Alright, so this next step is going to take a little bit of thought. So we have this equation we just found, 2 times the mass of the particle times v in the x. That's not going to change, remember, because they're elastic collisions. But remember, the right-hand side is the force of the particle, of the wall on the particle during this very tiny time of collision. Well, if I increase delta t, or increase the force, the other one has to go down, because they have to be inversely related, so that no matter how they multiply out, we get the same number here. Okay, well, if I'm going to do that, let's change this a little bit. Let's no longer look at delta t, which is just the time of the collision. Instead, I'm going to look at a much bigger delta t that I'm going to call delta t, between collisions of a single wall, which sounds a little crazy. What I'm saying is I'm going to look at the time that it takes this particle to collide, go over to this other wall, and then come back and collide with the same wall again. So this is delta t between collisions with a single wall. Okay, couple things here. First off, we're going to call the length of every side of this cube L, because it is a cube. And additionally, though, if we do this, and let me go ahead and substitute, I'm going to leave the left-hand side of the equation the same. So we're going to have delta t BCSW between collisions on a single wall. And if we do that, well, the force has to go way down, right? Because we've gone between having a tiny time of a collision with a wall with a much longer time, because it has to go all the way to one wall and back. So we can now say that this is the average force in the x direction from the wall on the particle throughout that entire time period. So we're no longer looking at just the time of collision, we're saying that's the average force, because most of the time the force would be 0. It's only going to experience forces when it hits here, so we're going to say it's the average force over that whole time period. Okay, now from here, let's do one more thing. So I have length L, I have delta t between collisions of a single wall, and remember, this particle is moving at some Vx. Well, I can relate these three together using our standard old velocity equation. That velocity is equal to delta x over delta t. But I'm going to change this up a little bit. I'm going to say that the v in the x direction is equal to, well, it's going here and back, so that's going to be 2L over this whole time, delta t between collisions with a single wall. And I'm now going to rearrange this a little bit and stick it way up in here. So if I do that, I'm going to have to multiply that and divide that across. So now I'm going to have this equal to F average x times now 2L over Vx, because I multiplied the delta t across divided by the V. And if I do that, we can now simplify a little bit more. So I'm going to go ahead and bring this down. 2mvx, we can get rid of the 2's. They just cancel out. And additionally, I can multiply the vx across. So I get mvx squared equals the average force of the whole time period in the x direction times L. So we've now reached this step, but this was only for a single particle moving back and forth in the x dimension of the cube. But there's not just one particle of gas. We have a rather humongous, probably, n number of particles. So now we're going to pretend like this gas is made up of n particles, but they're all still limited to only moving in the x direction. So they're going to go back and forth. They're not going to do anything else. Well, first off, I need to multiply both sides of this equation times n. So now I'm going to have nmvx squared is equal to, and then n times f average in the x times L. But additionally, we want to make something real clear here, that originally this was the velocity of a single particle, but now that we have all these different particles, they're not all going to be moving at the same velocity. So instead, I'm going to say this is the RMS velocity squared. Remember, this is the same thing as just really saying the average, just a different way of finding average. So the RMS velocity squared, the RMS velocity squared, that's correct. So now if I do this here, let's simplify things. Well, we can't really simplify things, but let's take it a further step. Now recall, let's say I multiplied one side of this equation by 1 over 1. Well, that is totally legitimate because that's not going to change anything, right? If you multiply anything by 1, it's the same thing. But I could make the top and bottom of this anything I want as long as both halves are the same, because anything divided by itself is 1. So I'm actually going to make this L squared and L squared, which might look a little bizarre, but let's now rearrange this a little bit. So now I have nm vx squared RMS is equal to n f average times the x. So L times L squared is L cubed over L squared. Okay, why did we bother doing that? Well, first off, remember that L is the length of the side of the cube in each dimension. So L cubed is simply the volume of the cube. Additionally, let's look at this. I have a force, average force of the wall, between the wall and the particle, divided by L squared, but L squared would be L times L. L squared would be the area of a single side of the cube. And that force divided by that area would be the pressure of a single particle of the gas. But multiplied by N would be multiplied by all the particles of the gas. So at this point, what I end up having is Nm Vx squared Rms. And now this whole part here is equal to the pressure. And this right part, L cubed, is equal to the volume. So now we've gotten to this point, and we have to remember, though, that these were for particles that were moving only in one dimension. But they can really move in 3 dimensions, x, y, and z, so we don't want just Vx squared, we have to include Vy squared and Vz squared. And doing that, when I change this to a mode that incorporates all 3 dimensions, so now I just have Vrms squared, I don't have an x anymore, it's all 3 dimensions now, I have to similarly multiply my right-hand side by 3, because now we are moving in 3 dimensions. Alright, almost done. And if I look at P times V, that should be ringing some bells, because we know from the ideal gas law, which is either PV equals little n RT or capital N KB times T, that I'm going to end up with something like this, and I can substitute in for PV this factor. So now I will have Nm Vrms squared is equal to, we'll leave that purple, 3 times NKBT. And lastly, I'm going to do one small mathematical trick. I'm going to divide both sides by 2. And additionally, we already see here that the ends are going to cancel. And when I do that, I am now left with, let me pick a different color here, 1/2 mvrms squared is equal to 3/2 times Boltzmann's constant times the temperature. And we know this is the average kinetic energy of a single particle. And congratulations, after all of that, we have finally gotten a derivation for this equation. I'm never going to ask you to do this, but I at least want you to be familiar with where it comes from, because every equation shouldn't just come out of thin air. They all have a reason for why they exist. They've all been derived in some form.